Now, what we have to understand is if this transition integral is going to have some value or not. So meaning that these integrals are going to have some value or not. So we can divide each term and then think about if each term is going to have some value or not. Okay. So let's think about from the easy one, which is a spin integrable for spin. So here, in terms of C, the spin, this suggests that the initial and the final spin quantum number is the same or not. So as you see, the ground state, a pair of electrons are occupied in the single state, which gives the spin the singlet state, right? Well, after photoexcitation, so one of the electrons excited to the higher energy level, but you'd know that there are two types of electrons possible. One is upspin and the other is downspin. So as you see, in this case, S equals 3, triplet state, and then this one is a singlet state. So thus, if the spin state is same, this is allowed, meaning that this integral values have some values. And on the other hand, if the spin state is changed from singlet to triplets or triplet to singlet, it is basically forbidden. So this integral is going to be 0. So this is quite simple. The spin state is remain or not. And in terms of B term, which indicate that the motion, due to the motion of the nuclear, so as you could see, if you remember that the reaction coordinate case, just simply think about diatomic molecules, which is connected by a spring, as I mentioned. So you've already studied the ground state and the excited state shows these kind of like energy levels. But you remember that so each of the vibrational states, there are vibrational states in the ground state and excited states too. And in each vibrational state, there's some a wave function. So that gives some sort of the probability of the states in each distance between these molecules. So in the light absorption, it's actually mostly start from the V equal 0, right? But because of the Frank quantum principle, it's going up to V equal N, means not 0. So not only the electronic state overlap, but also some vibrational wave function must be overlapped in the case of the transition, meaning from the V equal 0 of ground state to V equal N of S1 state. And this probability depends on the vibrational wave function, which is shown like this. Like this curve. So in this case, from v equals 0, and then this one is v equals 2, and 1, and then there's a edge of the v equals 1 in this drawing. So depending on this overlap, the integral value of v is going to be changed. Okay. And finally, and this is the most important term which we have discussed, is about A term, which is the wave function of electrons, initial and final, and you have some Hamiltonian. It's a perturbation Hamiltonian due to the light irradiation. And in this case, I will show one of the Hamiltonian explicitly and then which is E times X, meaning in the case when the light has a polarization in the X direction. So it's just simply the elementary charge times X. So let's think about like this, a simple example for the pi bond case. Here's the pi bond of the p orbitals aligned in the X direction like this. And then we are going to think about as a final state, it's like anti-bonding orbital aligned in the X direction like this. And then we are going to think about the polarization, the polarized light in X direction like this. And in this case, we just need to think about the E times X like this. So it's a line in the plane of X and Hamiltonian, right? So what we have to understand is that multiply these three terms, and if this integral is going to have some value or not. So that's what you have to understand. And to understand this, you have to understand again that it's kind of a reminder that you have to understand that we can judge if the integral is going to have some value or not. Is, for example, if it's like y equal x squared, it's going to have some value because the integral of y dx is going to non-zero, right? But if y equal x cube, these shadows are cancelled, so y dx equals 0, right? So even function, if the function becomes even, it's going to have value, but if it's odd function, it's going to be 0. This is one thing. And the second thing is you have to understand even function times even function gives an even function, right? Because x squared times x squared x force, it's an even function. Even function times odd function gives the odd function. And also add function times odd function gives even function. So these are the necessary information if you when you judge if the integral is going to have some value or not. Okay, so let's check based on this. What? So this one, so just looking in the x direction, we are going to take the derivative in the x, take the integral in the x direction. In the x direction, this function, this is a function of the even function, right? And in this linear function is an odd function. And then this anti-bonding orbital, it looks like an odd function. So by multiplying these three, so even times odd is becoming the odd function, and odd function times odd function is going to be the even function, right? So it means this integral have some value. So meaning that this transition is possible. So like this, you can understand that the transition is possible or not by judging if the integral is going to have some value or not, okay? And then, of course, this is a kind of easy, instinctive understanding how the light absorption is possible or not. However, even for this very kind of fundamental molecular orbitals, we have to think like this. And then not always we can judge this shape is even or odd. It's impossible for complicated molecules. But don't worry, we can judge by using the very useful theory called group theory to understand if this kind of symmetry is valid or not. And by just using the symmetry of the shape of molecules or even molecular orbitals, we can categorize them, and then we can use them for understanding the various physical properties of the molecules. And let's study about that in the next lecture. So with that, let's finish this chapter.